Infinite limits and vertical asymptotes. Let's begin by defining infinite limits. Or when do we use infinite limits? Now, infinite limits and vertical asymptotes will help us describe the behavior of the function that are unbounded near a particular x value. For instance, let us consider the function 1 over x minus 1. That function has the given graph here. Now, let's examine the behavior of the function. As x approaches 1 from the left, we see that the function continued to decrease, and it decreases without bound. So the function approaches the line here, and it will just continue to approach that line without end. So we say that the limit of the function as x approaches 1 from the left is equal to negative infinity. So if the function decreases without bound, that means the limit is equal to negative infinity. Or we would also write it this way. F of x goes to negative infinity as x goes to as x approaches 1 from the left. Similarly, if you look at the behavior of the function as x approaches 1 from the right, the function will approach the line here, and it will continue to do that without bound. So the function values increases without bound. In this case, we say that the limit of the function as x approaches 1 from the right, because the values are coming from the right side of 1, is equal to infinity. That means it increases without bound. Or we would also write it as f of x, which is equal to 1 over x minus 1, goes to infinity as x approaches 1 from the right. Now the line here where the function values is approaching to is called the vertical asymptote. And we write the equation for the vertical asymptote as x equals a constant, which is a vertical line. Now in this particular example, the vertical asymptote is the line x equals 1. Now the vertical line x equals a is a vertical asymptote of the graph of f of x if f of x approaches infinity or f of x approaches negative infinity as x approaches a from the right or as x approaches a from the left. That means if either one of these scenarios occurs, then that x equals this constant here is a vertical asymptote. Now consider the graph here and find the limit of the function as x approaches negative 3 from the left. This is negative 3. From the left is this one here, and we look at the function values. The function values approaches to this line here. It continued to grow or increase without bound. So therefore, this means that the limit of the function as x approaches negative 3 from the left is positive infinity. And similarly, if you look at the limit of the function as x approaches negative 3 from the right, the function values approaches this line here, and that continues to increase without bound. So that means this is also equal to positive infinity. Now, since both of these approaches to positive infinity, then we say that the limit of the function as x approaches negative 3 is equal to positive infinity. Because you see both of them are equal to positive infinity. So that's positive infinity. So it exists, and it's equal to positive infinity. Now for the limit as x approaches 2 from the right, from the right of 2. So it is these values here. So from the right of 2, your function values continue to decrease without bound. So we say that the limit here is negative infinity. And for the limit of the function as x approaches 2 from the left, your function values continue to increase without bound. So it goes to positive infinity. Now, if you want to evaluate the limit of the function as x approaches 2, so without the sign, that means you consider both right and left hand limit. Now, both of these are infinity, but the signs, this one is negative infinity, and this is also positive infinity. The two are not equal. They're not the same. So therefore, we say here that the limit of the function as x approaches 2 does not exist. And so for the vertical asymptote, we will get the equation for the line here. This is the line x equals negative 3. And this line here is also a vertical asymptote, and that is the line x equals 2. Now also, if you notice, these expression here are actually the points here. And notice that as x approaches negative 3 from the left, it's equal to positive infinity. Even without computing this, you can immediately say or conclude that x equals this number here is a vertical asymptote. And similarly, for the case at x equals 2, if you look at the limit of the function as x approaches 2 from the right, and we found out this is equal to negative infinity. At this point, we can then immediately say that the line x equals 2 is a vertical asymptote. In other words, we only need one side of the limit to approach either positive or negative infinity for us to conclude that a function has a vertical asymptote. And the equation of that vertical asymptote is of the form x equals a, where a is the value of x, where the x values are approaching to. Now, for instance, we are given an expression. How do we find the vertical asymptote? Now, it's important to take note that a polynomial function have no vertical asymptotes. And a vertical asymptote of a rational function can only occur at the 0 of its denominator. So consider the theorem here. For instance, you have a rational function of this form here, and d of c is equal to 0, while n of c is not equal to 0. Then in this case, we say that the line x equals c is a vertical asymptote of the graph of f. It's important to take note here that the vertical asymptote is the value of x for which the denominator is equal to 0, but the numerator is not. That means that if that particular x value makes both your numerator and denominator equal to 0, then that is not a vertical asymptote, but rather it is a hole on a graph. So for example here, let's describe the behavior of the function at each 0 of the denominator using negative infinity or positive infinity when appropriate. That means let's find the limit of the function at the zeros of the denominator. So for instance, in this first function, let's find first the 0 of the denominator. We have x squared minus 1 equal to 0. Then you solve for x. X squared is equal to 1. That means x is equal to plus or minus 1. Next, let's go ahead and evaluate the limit of the function at these values of x. Say, for instance, we evaluate the limit as x approaches 1. Now remember that the function is undefined at these values of x because the denominator is equal to 0 at these values of x. So since our function is undefined at that particular value of x, then when we evaluate the limit, we would be looking at the left-hand side and the right-hand side of these values of x here. Our function is defined at the left-hand side or the right-hand side of these values. So let's look at the right-hand limit as x approaches 1. Then we evaluate that by plugging in 1 to the expression here. So when we plug in 1 to the numerator, we get 1 squared plus 1 minus 2 divided by 1 squared minus 1. The numerator is 0 and the denominator is also 0. So we get an indeterminate form. We know graphically that if we have this type of scenario, this is the case when there is a hole on your graph. So that means at that point, at x equals 1, there's a hole on the graph. And we have seen an example where the function has a hole on the graph and the limit still exists. And the technique that we learned when we have an indeterminate form is to factor. So let's go ahead and factor both numerator and denominator. So let's factor the numerator. You have x plus 2 times x minus 1. And then the denominator is x minus 1 times x plus 1. Now, x minus 1 is a common factor, so that means you can cancel this. So cancel that. Therefore, to evaluate the limit, we will just evaluate the reduced expression, the equivalent expression of x plus 2 divided by x plus 1. And then you plug in. So let's plug in. We have 3. So 1 plus 2 is 3 divided by 2. So the limit here is 2/3. Now, since this results to a hole, we know that if we do the same thing, if we evaluate the limit as x approaches 1 from the left, so if we do the same thing, we will get the same value. So limit as x approaches 1 from the left, you get the same value. You do the same thing, you simplify this. You will be able to reduce it to x plus 2 over x plus 1, and that gives us the same value, which is 3/2. So in this case, we say that the limit of the function f of x as x approaches 1 is equal to 3/2. Next, let's consider the limit of this function as x approaches -1 from the left. Now let's begin by plugging in -1 to the numerator. So if you plug in -1 to the numerator, you have -1 squared minus 1 minus 2, and the denominator is 0. Now the numerator is -1 squared is 1, minus 1 is 0, minus 2 is -2. Then the denominator is 0. Now, this is not an absolute 0 because we're looking at the limit as x approaches -1 from the left. So we do that by plugging in some values here. And then let's just look at the sign. So we get a representative point for the values at the left side of -1. So as x goes to -1 from the left, so this is -1, this is -2, this is 0. The values are coming from -1 from the left. So you get a representative point here. Don't get -2 because that is considered far from -1. You get a value very close to -1 from its left side. So let's say, for instance, let's take a look at -1.1. Now, if you square -1.1 minus 1, the square of -1.1 is a value greater than 1. so that negative 1.1 squared is greater than 1 minus 1 will be greater than 0. So that means the 0 here has a positive sign. That means the y values, or the values here as x approaches negative 1 from the left, are coming from the right side of 0, or positive values. So that's why we put a plus sign here. So negative 2 over 0 plus is equal to negative infinity. So remember, if you have a constant over 0, the answer there is either plus or minus infinity. And the sign, it follows the rule of signs. So like in this case, the numerator here is negative and the denominator is positive. Negative over positive is negative. So we have negative infinity. Likewise, you do the same thing for the limit of the function as x approaches negative 1 from the right. And then you plug in, so you will have the same negative 1 in the numerator. And then the denominator is also 0. And then we will identify what the sign for the 0 in the denominator by getting a representative point at the right side of negative 1. So at the right side of negative 1, so it's coming from 0 going to negative 1, that may be negative 9.99. So now negative 0.99, if you square that value is less than 1. Minus 1, that means the answer is negative. So that is less than 0. So negative 0.99 is a positive value, but it's less than 1. Minus 1 will be negative. Or you can also use your calculator and plug in the value and just look at the sign. Now you have a negative expression. This one would result to a negative value. So that means the 0 here are coming from the negative side. So you have a 0 minus in the denominator. So negative 2 over 0 from the left is equal to, so negative over negative is positive. So this gives you positive infinity. So the limit of the function as x approaches negative 1 from the right is equal to positive infinity. Now, since the left-hand side, one of the left-hand sides, or actually both, so this one goes to negative infinity and this limit here goes to positive infinity, then we conclude that x equals negative 1 is a vertical asymptote.